We'll now see the question shown on your screen. Consider a system as shown in the figure, in which a liquid B moves slowly through a slightly soluble porous plug of A. Then A slowly disappears by a first order reaction after it has dissolved. If DAB is the diffusivity of A in B, find the steady state concentration profile of A in the axial direction of tube upward from the plug. Assume the velocity is flat across the tube. Ca0 is the solubility of unreacted A in B. Neglect temperature effect associated with heat of reaction. Consider the kinetics of reaction as shown below. A gives C, which is a first order reaction, and the rate of the reaction is minus K1 triple dash Ca. Now we'll first see the figure. The reaction is as follows, and the rate is given by triple dash Ca. Now the equation of change for a multi-component system says that rho d W alpha by dt is equal to minus del dot J alpha plus R alpha, where d alpha by dW alpha by dt is the substantial time derivative of W alpha. Now we have three options. Either we can use Cartesian coordinates, that is x, y, z, cylindrical coordinates as r theta z, or spherical coordinates as r theta phi. In the problem we have been given a cylinder or a pipe, so it's more logical to assume cylindrical coordinates as r theta z, in which the equation of change becomes as follows: rho times dou W alpha by dou T plus Vr times dou W alpha by dou R. Now we have three options. Either we can use Cartesian coordinates in x, y, z, as in Cartesian coordinates the equation becomes rho times dou W alpha by dou T plus Vx into dou W alpha by dou x plus Vy into dou W alpha by dou y plus Vz into dou W alpha by dou z is equal to minus of dou J alpha x by dou x plus dou J alpha y plus dou y plus dou J alpha z by dou z plus R alpha. The equation of change in cylindrical coordinates, that is in terms of r theta and z, becomes rho times dou W alpha by dou T plus Vr times dou W alpha by dou R plus V theta by R times dou W alpha by dou theta plus Vz times dou W alpha by dou z is equal to minus of 1 by R dou by dou R of R J alpha equals minus of 1 by R dou by dou R of R J alpha R plus 1 by R times dou J alpha theta by dou theta plus dou J alpha z by dou z plus R alpha. The same way it follows with spherical coordinates in terms of r theta and phi, as you can see on the screen. Now, to obtain corresponding equations in terms of capital J capital J alpha star, we can make the following replacements. We can replace rho by C, W alpha by X alpha, J alpha by capital J alpha star, V becomes V star, and R alpha becomes R alpha minus X alpha times summation of beta is equal to 1 to n R beta. In the question, it has been given that we have to find the steady state concentration profile of A in the axial direction of tube. A tube is a cylinder, so it's purely logical to assume cylindrical coordinates rather than assuming Cartesian coordinates and spherical coordinates, and to complicate the problem even more. Though solution can be obtained by these coordinates, it would be more tedious task than to do it using cylindrical coordinates. So in terms of cylindrical coordinates, that is r, theta and z, we have the equation rho times dou w alpha by dou t plus Vr times dou w alpha by dou r plus V theta by r times dou w alpha by dou theta plus Vz times dou w alpha by dou z is equal to minus 1 by r dou by dou r of r j alpha r plus 1 by r times dou j alpha theta by dou theta plus dou j alpha z by dou z plus r alpha. As I had told previously, we can make the replacements to obtain the equations in terms of capital J alpha star. After replacing the above equation with the terms I had shown previously, we get the following equation: C times dou x alpha by dou t plus Vr star times dou x alpha by dou r plus V theta star times V theta by r times dou x alpha by dou theta plus Vz star times dou x alpha by dou z is equal to minus times 1 by r dou by dou r of r j alpha r star plus 1 by r times dou j alpha theta star by dou theta plus dou j alpha z star plus dou j alpha z star by dou z plus r alpha minus x alpha times summation of. Now we'll write the equation in terms of A, because we have to find the steady state concentration of A. So replacing XA with CA by C, and C gets cancelled throughout because C is outside the bracket, we take it common, it gets cancelled throughout, and the term summation beta is equal to 1 to n r beta becomes RA plus RB plus RC. As beta is from 1 to n and n here is 3, the components A, B and C. Also X alpha becomes XA. So we get the final equation as dou CA by dou T plus VR star times dou CA by dou R plus V theta star by R times dou CA by dou theta plus BZ star times dou CA by dou Z is equal to minus of 1 by R times dou by dou R of R DAB times dou CA by dou R plus 1 by R times dou by dou theta of DAB times dou CA by dou theta plus dou by dou Z of DAB times dou CA by dou Z plus the change term, which is minus XA times RA plus RB plus RC. So the term dou CA by dou T becomes 0 because we have assumed steady state. Also because we have to calculate steady state concentration of A. VR star is 0, so this term also becomes 0. B theta is also 0, so this term also becomes 0. Now this term isn't changing with R, so this becomes 0. It doesn't change with theta, so this becomes 0, and we will be left with this term only. Also the rate at which A is being consumed is the same as rate at which C is being formed, and B is not taking part in any reaction, so this term also becomes 0. So the final equation after implementing these changes becomes VZ star times dou CA by dou Z is equal to minus dou by dou Z of DAB times dou CA by dou Z plus RA. Now let us assume VZ star is equal to V naught, and also we have been given in the question that RA is equal to minus K1 triple star CA. Substituting these in the above equation, we get V naught times dou CA by dou Z is equal to minus DAB times dou square CA by dou Z square minus K1 triple prime CA. Oscar. We have the boundary conditions as at Z equal to 0, we have Ca as initial concentration Ca naught, and at Z equal to infinity, the concentration of A becomes 0. Substituting these boundary conditions and Oscar. Now for this question, we have the following boundary conditions. At Z equal to 0, Ca is Ca naught, and at Z is equal to infinity, Ca is 0. The equation V naught times dou Ca by dou Z is equal to minus DAB times dou square Ca by dou Z square minus K1 triple prime Ca is a standard differential equation of the form Now we divide the whole equation by DAB. So we get dou square Ca by dou Z square minus Vz by V naught by DAB times dou Ca by dou Z minus K1 triple prime by DAB times Ca is equal to 0. Now let us assume that A, which is a constant, is equal to minus Vz by DAB and D is equal to minus K times DAB. So the above equation becomes a standard linear ODE of the form d square y by dz square plus a dy by dz plus by is equal to 0. This is a homogeneous second order linear differential equation and the solution depends on the roots of the characteristic equation n square plus an plus b is equal to 0. Let the roots of this equation be n1 and n2. If real and distinct, we get y is equal to c1 e to the power n1x plus c2 e to the power n2x. If real and equal, we get y is equal to c1 plus c2 z e to the power nz. Sorry, I made a mistake here. It should be z, not x. If n1 and n2 are complex, we get y is equal to e to the power nz times c1 cos qx z plus c2 sin qz. We apply boundary conditions to get the values of the constants. So we get the final equation as Ca by Ca naught is equal to exponential of minus under root 1 plus 4k1 triple prime dAB by B naught square minus 1 into V naught Z by 2 dAB. So this is the solution for our equation.